I will present for Stage 1 System Modeling. To transition from theoretical equations to a working simulation, we first had to define all the concrete system parameters for our NEV and its operating environment. These values are essential for calculating the exact forces in the model, and by setting this physical constant, we ensure our model is a high-fidelity representation of our actual NVE platform. Our model was constructed in MATLAB Simulink using an integrator-based approach, but the core logic resides in a single function block that calculates the net force. Below here is our MATLAB coding, which the first one is parameters, second one is velocity simulation for ego and LICA, and the third one is linearization. Moving on with system modeling, the next code is system testing code. And from this code, we create a Simulink model. As you can see from the top picture, is our Simulink model architecture. This figure illustrates the overall closed-loop control architecture implemented in the Simulink. The system takes two primary reference input, the lead vehicle speed and the echo vehicle target set speed. A critical safety logic subsystem calculates the real-time distance gap by integrating the relative velocity between the two vehicles and compares it against a predefined safe distance. Based on this comparison, a switch block determines the control objective by maintaining the driver's set speed or braking to maintain a safe following distance. The resulting error signal is fed into a PID controller which computes the required torque command, and this command drives the drivetrain and vehicle dynamic subsystem which output the actual vehicle speed and position, closing the feedback loop. And the second picture is our vehicle drivetrain model, and this vehicle drivetrain subsystem models the electromechanical conversion of the controller signal into physical propulsive force. The input signal first passes through a saturation block which enforces the motor's physical constraint by clipping the torque to its peak limits. The signal then enters a first-order transfer function which simulates the transient response of the electric motor, introducing a time constant to represent the lag in electromagnetic torque build-up. Finally, a game block converts this rotational motor torque into linear traction force by applying the transmission gear ratio and efficiency and dividing by the whole wheel radius. And the third picture is our vehicle dynamic model. And the vehicle dynamic subsystem implements the longitudinal equations of motion based on Newton's second law. A central summation block calculates the instantaneous net force by subtracting the resistive loads, rolling resistance, aerodynamic drag, and grade resistance from the input traction force. And crucially, the model utilizes a feedback loop where the current velocity is squared and multiplied by aerodynamic constant to dynamically update the drag force as speed increases. The resulting net force is multiplied by the inverse of the vehicle mass to derive acceleration, which is then passed through two integrator blocks in series to compute final vehicle velocity and position.
Moving on to stage 2, we conducted the open loop simulation. Before we could design a complex controller like the ACC, we first had to understand the natural behavior of our NEV. To do this, we applied a step input to the throttle. In simple terms, we simulated flooring the gas pedal, going from 0 to 100% throttle instantly. We mean to observe how the vehicle's acceleration curve behave without any computer interference. This gives us the baseline performance you see in the graph on the left. If you look closely at the force time history here, the yellow line represents our motor traction force. You can see it jumps to it peaks immediately because we applied full throttle. However, the interesting part is the blue line, which represents the resistive forces, primarily aerodynamic drag. As mentioned in the green section on the right, this force is non-linear. You can notice how the blue line curve outward, right? This confirms our mathematical model, which is aerodynamic drag increases quadratically with speed. The faster we go, the exponentially harder the air pushes back. This also includes rolling resistance, which stays relatively constant, but it is the air drag that drives this curve. This interaction leads us to the concept of dynamic equilibrium, which I have highlighted in the pink section. At the start, t equal to 0, we have maximum acceleration because the drag is 0. But as the blue resistance line rises, it starts eating away at our net force. Eventually, if we let the simulation run long enough, that blue resistance line would rise to meet the yellow traction line. At a specific intersection point, the net force becomes zero. This is where the vehicle hits terminal velocity. It physically cannot accelerate anymore because the motor is using all its power just to overcome the wind. Finally, looking at the blue section, we analyze the system stability type. The response we observe is smooth and overdamped. You don't see the speed oscillating or shaking, it simply just rises and settles. This is a crucial finding for our project. It proves that an EV is naturally stable. It means that friction and drag act as natural brakes. If we cut the power, the system naturally returns to a stable state, which means rest rather than diverging. Knowing this confirmed that our physical plant model was realistic and safe, giving us the green light to proceed to stage 3, which is designing the PID controller to manage this response. That's all from me. Thank you.
We will move on to stage 3. So stage 3 involves the stability analysis of our vehicle dynamic model, which begin with linearization to simplify the non-linear system. So the linearization process was performed using a state space formulation, which is a Jacobian matrix ABCD around a key operating speed of 6.94 meter per second, approximately 25 km per hour. So the primary finding was that the open loop system is naturally stable. So this stability is evidenced by the system matrix A having real and negative eigenvalue. Physically, this means that passive damping force such as friction and air drag dissipate energy, ensuring that if the throttle is removed, the vehicle naturally returns to rest without exhibiting undesirable oscillation or divergence. In stage 4, we move to the controller design for the adaptive cruise control ACC system, employing a cascade control loop consisting of an inner loop and an outer loop. So the outer loop handles distance control, that measuring the gap to the lead vehicle to adjust the driver's seat speed or set a lower reference velocity to maintain spacing. So the inner loop performs speed control using a PID control to compare the reference velocity with the actual velocity and compute the required motor torque command. So our initial implementation faced a challenge where the PID output was ineffective due to a motor saturation block set to low, which was corrected by increasing the motor specification to greater or lower 16 Newton meter, which is the upper limit is 60 Newton 60 and lower limit is negative 60. So the final PID tuning value were proportional, which is Kp equal to 1 for moderate spikes free response, and for integral Ki is 0.05 for lower gain to eliminate steady state error, and for derivative Kd 0.5 to dampen the response and reduce overshoot during speed transition.
So moving into stage 5, which is validation and robustness, this is where we prove our tune controller actually works. We tested the system against a dynamic follow the leader profile, where the lead vehicle accelerated and decelerated between 0 and 10.5 meter per second. Our goal was to meet 3 performance criteria, which is minimize overshoot, eliminate steady state error, and most importantly, maintain safety. Looking at the speed graph, we can see the results. The actual NEV response, which is blue line, tracks the ACC generated target, which is yellow line, with exceptional accuracy. This confirms our integral gain, Ki equals to 0.05, successfully eliminated the steady state error. The initial acceleration, which is 0 to 5 seconds, is smooth. Then, the overshoot was reduced to an acceptable level of less than 5%, validating the effectiveness of our derivative term, which is Kd equals to 0.5, in ensuring passenger comfort during rapid speed changes.
But the most critical job of adaptive cruise control is safety. We rely on the outer distance loop to maintain a safe gap. Figure 7 shows the relative safety distance error. The delta x value, which is the difference between the actual distance and the required safe distance, remain positive for the entire simulation. This means we maintain the required safe stopping distance at all times. Notice on the previous graph, during acceleration, the ego vehicle, blue or yellow, maintained a slightly lower speed profile than the lead vehicle, which is orange. This wasn't a failure to track, it was the outer loop functioning correctly, and it intentionally created a velocity deficit to build up that essential safe following distance before matching the leader's speed. Furthermore, even during the heartbreaking event, the controller reacted quickly enough to prevent the gap from dropping below the safety threshold. As for the robustness test, by including negative torque limits, specifically negative Newton meter, the vehicle was able to actively brake when the lead vehicle slowed down, which, preventing collision, a crucial requirement for any ACC system. The system tracked down all dynamic changes in the leader's speed with a time lag of less than 2 seconds. So in conclusion, the adaptive cruise control system for the 490 kg NEV successfully met all design objectives. We identified and overcame a critical challenge. The initial poor performance, overshoot and slow response was traced back to an incorrect setting in the motor saturation block. By correcting the actuator limits to plus minus 60 Nm and implementing the tuned PID values, we achieved stable and accurate tracking. The simulation confirms that the NEV can now operate autonomously and safely within its operational range, maintaining both speed and crucial safety protocols. This project successfully translated the nonlinear dynamics of a vehicle into a robust closed-loop control system. Thank you.